Today we're going to talk about the Cannonball Run and basically how that ties in with physics, with speed and velocity. Okay, you might not be familiar with it. The Cannonball Run, they made a movie back in the day, but basically it's this journey, or maybe even a stunt you would say, from driving from New York City to California in as fast as you can. So it's a 2,800 mile journey. The latest person to do it, actually a group of guys to do it, their nice little Audi S6 I believe, they traveled at a rate of, get this, 110 miles per hour. That was the average. I think they only stopped once, maybe even twice. So you do the math on how that worked out. Pretty insane of a trip. Okay, now let's talk about it. What does that have to do with physics? What does it have to do with speed and velocity? Speed is really the rate at which something travels, or another way to say that is the distance that something would go in a certain time period. Take, for example, you're going down the road, hopefully at a normal speed, say 55 miles per hour. That is a speed that we know. It's a rate. So we're saying that if we were to drive for an hour at that same speed, we'd end up going 55 miles. Or if we did it for 2 hours, we'd end up going 110 miles. So it's the rate at which we're traveling. We might see that beyond just the speed limit sign. So maybe in a baseball game, right? It's a fast pitch. You see that little speed monitor tell you how fast it's going, right? If you're maybe watching a tennis match, so you watch the serves, how fast is that going? We look at all sorts of things, race car, NASCAR, you name it, that we're looking at the speed. So let's take a look at exactly how do we find that speed and what's the equation. Now, the equation for it is speed equals distance over time. A good way to think about this, so 55 miles per hour is a speed, we know that. If you look at it, miles is a distance, per is like division, and then we have that time, hours, on the bottom. So it's like the miles over, right, are hours, or miles per hour. Now, in science, we typically use meters as our distance, and we use seconds as our time. Now it really translates into whatever project, whatever equation we're doing, whether we're converting or not, but typically we use meters per second when we talk about physics and we talk about our general problems here. But hang with me, let's do a couple of problems with this to make sure this makes sense. Before I jump into it though, most of the time when we're finding our speed, it's an average. What I mean by that is, say I'm in a foot race. I'm starting at the start line, I run my distance in a certain amount of time. If I find my speed, that's an average because think about it, at the start of the race, I was probably going 0 meters per second or miles per hour. At the end of the race, I may have been going the fastest. Or maybe I changed my speed throughout the race, so I end up finding an average. There is something called instantaneous speed. This is kind of like if I had a radar gun, I was like, boop, and I clocked myself at an exact second. That's what we call instantaneous speed. So at that exact second, what was my speed? It's a lot harder to calculate. This is typically why we find averages. So let's take a look at a couple problems. Our first problem. All right, so we have Edwin. He's a racing camel, okay? Edwin took off through the desert and he went 1,600 meters, okay? We have a distance. If it took Edwin 4 minutes, what was his speed? Okay, so we have our distance, we set up distance, 1,600 meters over our 4 minutes. In this case, we're not going to change any conversions. Let's keep this super simple. So 1,600 meters divided by 4 minutes, and we end up getting, hopefully you know, 400 meters per minute. Now we could change that again, we can convert it. We're not worried about that today, but that would be the speed. So we have how fast the camel went on average. Okay, our next problem for you. All right, so we have Jimmy and Timmy who ran different events at track and field. Clearly they want to know who was the fastest, right? Jimmy ran the 200 meters in 40 seconds. Timmy ran the 800 meters in 80 seconds. So let's take a look at their average speed. So first off, let's look at Jimmy. We set up the equation, 200 meters divided by 40 seconds, and we end up getting what? So 200 divided by 40, we end up with, hopefully you know, 5 meters per second. Now let's take a look at Timmy. He ran 800 meters in 80 seconds, so we have 800 meters, the distance, divide that by the time, and we end up with what is it? 10 meters per second. So if we're looking at that, which one's faster? Obviously the rate of speed is actually going to be Timmy running 10 meters per second versus, again, Jimmy, who only ran 5 meters per second. So a big change there. So who's our overall winner? Timmy there in that problem. Now, we've talked about speed. So speed is basically a rate of movement. Now, what is velocity? How is that any different? Is that just the physics term for speed? Yes and no, all right? Really, the difference is velocity includes a direction. So in a car, say you're going 10 miles per hour, in the car, you could be going forward, you could be going backwards, whether you're going in reverse, you can be going east, you can be going west. That is just a blanket absolute value. When we look at velocity, this actually has direction. So if I say a car is moving 10 miles per hour, I need to add a direction. So if that's going forward, if it's going east, if it's going west, it also does add in this another kind of little feature. We can add a negative in there. So if I say a car is moving negative 10 miles per hour, it's moving in the opposite direction that maybe it was previously going or that we're assuming. So if 10 miles per hour is moving forward, negative 10 miles per hour is actually moving backwards or in the opposite direction. So the problems, the equations are all set up the same. It's velocity equals distance over time. So it's the exact same. So if I just take out the word speed and add in velocity, it's still distance over time. The only change, again, you need to add a direction. Okay, let's look at a sample problem. So here we have a bicyclist. He's going to be traveling 60 kilometers and it takes him 2 hours. What would be the average velocity? We'll set it up, right? 60 kilometers is the distance over 2 hours. We end up getting 30 kilometers per hour. Now that would be a speed, so how do we change that into a direction? We would say maybe he's moving south, okay? So in this sort of equation, maybe we know the directions to the map. He's going southbound at 30 kilometers per hour. Now, I don't want to just always be using the same equation to find, say, speed or velocity. I could use the same equation if I had the velocity and maybe say I had the time, I could find the distance. Take, for example, this problem. If a baseball can be thrown at 12 meters per second, how far will it travel in 10 seconds? So now I have to set up the same equation. We have the speed or velocity of 12 meters per second. We have the time, 10 seconds, and what we're left with is we don't know what that distance is. So how do we figure that out, right? Now, those of you guys are very good at math. You can kind of realize, well, it's just 12 meters per second times 10 seconds, and we end up getting 120 meters. Those of you that need to look at the equation, right, what we need to do is we need to cross multiply, right? Our distance is going to be x. So we end up with 12 times 10 equals x, or d for distance, and we end up with the same answer, 120 meters. Now this equation we've been using does more than just solve for, say, velocity or, say, for distance. We can also use it to find time. So take, for example, if we had the average speed of Sam, who's on this bus ride, it's going 48 kilometers per hour. That's our rate of movement. And say his friend lives 72 kilometers away, right? So our variable here is how long would it actually take him to get to his friend's house. Maybe his friend's waiting, right? Maybe there's meatloaf on the stove. It's important. Okay, so let's take a look. So we have 48 kilometers per hour is our velocity, equals our distance, right? Which is, in this case, 72 kilometers over our time. So if we cross multiply, we end up getting 48t, t's being the variable for time, equals 72 kilometers. Now we can isolate that variable, 72 divided by 48, and we get 1.5 hours. Okay, we know it's hours because if we look at that rate, it said kilometers per hour, so we keep those units. So hopefully now you have an understanding of, one, what Cannonball Run is, but two, also what the difference between speed and velocity is. Speed, again, a rate of movement, versus velocity, which is the rate of movement with a direction, and sometimes that can be a negative number because we're going the opposite direction than we had previously gone. So instead of going forward, maybe backwards, or instead of east, now we're going west. Hopefully that was kind of eye-opening to you, and hopefully you'll do well on your next test if you need to know it. Thanks for watching.